Alright, so now I'm going to begin today by talking a little bit about random sampling error. So just to start off, I wanted to distinguish briefly the difference between random sampling error and sample variation. We're talking about sampling error. We're talking about the difference between a specific sample statistic that you would obtain after conducting a study and how that would relate to what is the true population parameter for whatever it is, of course, that you're studying. Compared to that, we have sampling variation, which is the difference between values found in different samples which have essentially been drawn from the same population. So you might do one study and then another study, and there would be differences between each of those studies and what is the true value in the population. And then there would be, of course, variation between the individual samples, study 1 and 2, for example. Okay, so when we're talking about sampling error today, we'll be specifically discussing random sampling error. And despite the fact that it's random, it actually is predictable, which is useful for us when we're discussing meta-analysis. And of course, small samples are going to be more likely to be unrepresentative of larger samples as far as what the true population, estimating the true population parameter. We can see here in this figure that as we increase our sample size, sampling error actually decreases. And this is a helpful thing to know. Of course, then we want to have as large a sample as possible so that we can have reduced sampling error and a better estimate of the population parameter. So this is an asymptotic relationship. As we increase sampling error, sample size decreases. As we increase our sample size, sampling error decreases. But however, as you could tell from the figure on the previous slide, there is actually diminishing returns to this. This is oftentimes why when they do political opinion polls, they only increase their sample size up to a certain point, because they would actually have to add, once they reach a certain point on the graph, you'd have to actually add thousands more people to actually decrease the sampling error, and you'd gain very little for it. But in addition to being based off of sample size, sampling error also is a function of the magnitude of the population value. So you actually don't need a very large sample size when the population value that you're trying to estimate is very large in magnitude. When I'm talking about magnitude, you could think of a very large correlation or a very large standardized mean difference, for example. Two illustrations of this. One, you might be interested in asking what percentage of Americans believe that drinking poison is a bad idea. In another example, you might consider asking the percentage of Americans that think eating earthworm ice cream is delicious. In both instances, you wouldn't have to sample very many people to get a pretty accurate estimate of what the entire population believes. So this is an example of how random sampling error is also a function of the magnitude of the population parameter. Okay, so because this is a random phenomenon, sometimes random sampling error is going to essentially cause us to underestimate a population value in our study. Sometimes we're going to actually overestimate the population value. So here, for example, you could see a distribution in the figure between two variables, and we can see here that in our hypothetical case, sample 1 would actually be representative of what the true population is. We might go out and actually collect though a second study, and we can see here that in this case, the second sample has a different estimation of this. Okay, so we've got a different value for the same phenomenon in our second study, and again, this is due to random sampling error. If we were to look at this phenomenon again in a third study, we might get a completely different value again. Okay, so this is due to the fact that it's random. So in some instances, we might get an accurate estimate. Other instances, we might get an overestimate or an underestimate. But thankfully, all of this is going to eventually average out. Okay, so as we go and collect more and more samples, the number of samples will eventually, the sample averages will eventually average out as far as what the true population parameter is. So to give you another illustrative example, I used to do a poker chip example in my research methods class. So I would put a grocery bag out for the students, and there would be typically 30 poker chips in there, and I'd have a ratio of 7 reds to 3 black poker chips. Poker chips. And so students would draw random samples. Sometimes they would draw a ratio of 6 to 4, other times 8 to 2. Sometimes they'd draw the true population of 7 to 3, and so forth. And what I would do is I would get out an Excel sheet, and I would add up everyone's random samples, and we would get an average of 7 to 3, showing how these random samples were actually a random phenomenon, and with enough successive samples you could get that random error to average out. Okay, so a couple of other things just to summarize. As I mentioned before, sampling error is going to be affected by both the sample size and the magnitude of the population. Larger samples will typically have less random sampling error, so of course we prefer larger samples. But with meta-analysis, as I'll talk about in just a moment, we can get these errors to average out. Because random sampling error is does not systematically affect the mean of the observed distributions of effect sizes, this is a good thing when we're doing a meta-analysis, because again we can get these things to average out over time, and we'll get a better estimate of what the true population parameter is. This will also come up again later on when we're talking about artifactual variance. Typically when we see differences between study estimates, sampling error is considered to be the primary reason why a lot of research does not appear to replicate, and another primary reason why we want to actually do a meta-analysis, and why we'd consider the results of a meta-analysis to be the best estimate of what's truly going on. So meta-analysis draws upon this sampling error theory. Each time we do a study, we're getting an estimate of the population parameter. Some are again going to overestimate the population parameter, others will underestimate, and we can get this ultimately to average out. And so we'll talk about actually going through the calculations for doing this when we get to the module on basic calculations for a meta-analysis. And that is the brief overview of random sampling error.